we're going to look at what we need to know about the cross product. So what should I know about the cross product? Well, much like the dot product, the cross product is only one method for multiplying vectors. The cross product is also known as a vector product because the result of that multiplication process is in fact a vector, much like what we experience in multiplication of numbers as well as other algebraic objects. The cross product has a geometric interpretation, and you can see that it's quite similar to what we saw with the dot product. The difference being that it's the sine of an angle of separation rather than the cosine of the angle of separation. We'll talk a little bit more about what this means, but for now we're going to leave this as kind of a symbolic representation, keeping in mind that there is more to this to come in class. The cross product is only defined for vectors in R3, so we cannot do a cross product of vectors in the plane, but we can do cross product of vectors in space. And the cross product can be found algebraically, and it's based on the determinants of matrices. So let's go ahead and see what this would look like. So to find the cross product algebraically, we set up a 3 by 3 determinant, looking something like this. So let's assume that we want to do the cross product of two vectors. The first vector being the vector 2, -1, and 4, the second vector being 3, 2, and 5. So we set up a 3 by 3 determinant, determinant being denoted by these vertical bars around this matrix. And in the first row we put the three standard basis vectors I, j, and k. In the second row of this matrix, we put the first vector that we've been given, and in the second row we put the second vector that we have been given. So we set up this 3 by 3 matrix. Now we start finding the determinant, and so we start by looking at the first row, and the first component of the first row is this unit vector I. So I pull out this unit vector I, and then I remove the row and column which contains the unit vector I. If I remove that row and column, I am left with a small 2 by 2 matrix containing -1, 4, and 2, 5. So now I set up a smaller 2 by 2 matrix containing that -1, 4, and 2 and 5. I move across the first row to the second entry, which is the unit vector j. And based on how we expand determinants, this j actually has a -1 coefficient. So we represent that as -j. And now I remove the row and the column that contains the unit vector j, leaving me with a small 2 by 2 matrix containing 2, 4, and 3, 5. Continuing across that first row, we get to the unit vector k. So we expand about that unit vector k, and we're left with, and we remove its row and column, and we're left with a small 2 by 2 matrix, 2, -1, and 3, 2. And so as we continue expanding, we've taken a 3 by 3 determinant and turned it into 3 2 by 2 determinants, which we should know how to expand. So now we're having this situation where I need to do unit vector I times the determinant of this matrix. So it's the product of the diagonal elements, so that would be -1 and 5, minus the product of the off diagonal. So minus the product of 2 and 4. Well, the product of negative 1 and 5 is negative 5 minus 8, and negative 5 minus 8 will give me negative 13. Continuing, I have minus unit vector j. The determinant of the 2 by 2 is the product of the diagonal elements, so that's 2 and 5, minus the product of the off diagonal elements, which is 3 and 4. So I have 2 times 5 minus 3 times 4. This is 10 minus 12, which is going to give me a negative 2. Continuing on to unit vector k, we are going to do this 2 by 2 determinant. So it's going to be the product of the diagonal elements, so 2 times 2, minus the product of the off diagonal, so negative 1 and 3. 2 times 2 is 4, minus negative 3. 4 minus negative 3 is 4 plus 3, or 7. So the cross product of the two vectors is negative 13, negative 2, 7. And this is written in the IJK format. You could also write it in the angle bracket format.